Welcome to the fourth part of Unit 6. In this unit, we're actually going to move on to Newton's second law. So in the first part of this unit, we laid the foundation with Newton's first law. And then in the next two parts, we've been discussing forces and way to organize forces. So we're finally ready to move on to Newton's second law. And in many ways, Newton's second law is very much a part of Newton's first law. It tells you what happens when there is a net force acting on an object. So Newton's second law tells us that the net force applied to an object equals that object's mass multiplied by its acceleration. So in other words, the net force, F net, equals ma. And remember this guy, F net, as we saw a couple parts ago, is the sum of all the forces applied to the object. And remember, by sum here we mean vector sum, so you got to watch out for directions. Okay, so F net equals ma, Newton's second law. For the rest of this this part, we're going to look at two specific examples, one bigger than the other. So the first example is we're going to go back and think about falling objects again, because we've spent a lot of time in this class talking about falling objects and objects undergoing projectile motion. And throughout all of them, we've ignored air resistance. Completely ignored air resistance. Okay, let's think about those objects now, both with air resistance included and without. And let's start in familiar territory. Okay, so if I have an object, maybe a ball, going through the air, and I neglect air resistance, then what forces act on this ball? Well, it's in the air, so nothing's touching it. Yes, something had to touch it to get it going, but it's now up and in the air, so nothing more is touching it. And the object's weight. And the weight is acting downward. So weight of Earth, let's call it a ball again, is the only force on this ball. And remember, that guy equals mg. By definition, weight equals mg. We saw that a couple parts ago. So now if I take Newton's second law and let F net equal ma, then I can now rewrite the net force in terms of the forces applied on the object. Remember, back in part 1, we had examples where we had a 5 Newton force this way and a 3 Newton force that way, and we said the net force was 2 Newtons in that direction. Same thing here, but instead of having a 5 Newton and a 3 Newton, all I have is a W. I have a variable instead of a number, if you will. So rewrite the net force in terms of the forces acting on the object. Remember, weight equals mg, which equals ma, and the m's cancel, and we get that the acceleration of the object in this case is just the acceleration due to gravity downward. Exactly the assumption we made when we were doing projectile motion in either 1 or 2 dimensions. But now let's think about what's going on with air resistance. And we've got two things we got to think about here. So I'm going to take and further subdivide this side. And the first one we're going to think about is, what about when the ball is moving upward? Okay, so I've tossed it up into the air. It's left my hand, so my hand is no longer touching it. And as it moves up to the pinnacle of its motion, what's going on with the forces? Well, now we have two forces. We still have gravity pulling downward, so that's weight of Earth on ball. And remember, in this case, the velocity is upward. Air resistance, being a type of friction, will be opposite, so the friction from the air on the ball will point downward. So in this case, I have F net equals ma. And I'm going to rewrite the net force in terms of the forces acting on the object. And I get that the weight plus the friction equals ma. Okay, now ball is moved up, it's hit the top, it stopped momentarily, and now it's coming back down. When it's coming down, that velocity vector is now downward. Okay, well, weight still points downward, but now the friction points upward. So if I take and write F net equals ma, again, I get the weight minus the friction equals ma. So in this case, here the acceleration has to be greater than g because we have mg plus another piece. Here, the acceleration has to be less than g because I have the weight, or mg, minus another piece. And if you notice, it's possible for the weight and the friction, the air resistance, to actually be equal, in which case the acceleration could be 0. And in that case, when acceleration equals 0, which occurs again when the weight equals the force of friction, in that case, the object is said to be undergoing terminal velocity. It is now falling at a constant velocity. Okay, so moving on to our next example. We're going to take a 60 kilogram person and stand them on a scale in an elevator. Because why not? And okay, so hold on a second. You see the word book. This is supposed to be person. I changed the slide a little bit and I screwed up. So what is the normal force on the person if the elevator is accelerating upward, the elevator moves at a constant velocity, or the elevator is accelerating downward? Okay. So first off, let's think about our elevator again. So here's our elevator. Here's the scale. It's a big one this time because I didn't go to the effort of drawing it small. There's the person standing on the scale. What forces are on that person? Well, the person's weight pulling downward and the normal force between the scale and the person, which in the last unit is the one we identified on the scale with the subscripts reversed. The scale actually reads this because that is the force that actually is on the scale. So we want to know, essentially, by asking these questions, what's the scale going to read when it's accelerating upward, when it's moving at a constant velocity, or when it's accelerating downward? Okay. Now, before we jump into that, let's identify where in the motion these accelerations and constant velocities occur. So let's consider a building with 3 floors. Oh, I don't know, kind of like Byrd Science Center. So we have the first floor, we have the second floor, and the third floor. Okay, so what's the first thing that happens? The elevator's at the first floor, you get in, you push the button and it starts moving upward. So initially V equals 0, and sometime later the elevator is now moving upward towards the third floor, which means somewhere in here we had to have an upward acceleration in order to make that happen. But eventually the elevator just, settles in for the long climb, if you will. So somewhere in here we get a constant velocity piece as it moves up. But, all good things have to change, and we need the elevator to stop at the third floor. Otherwise, bad things happen. So we go from having a velocity to back to 0, which means here the acceleration is downward. And I forgot to say the constant velocity case, remember, is a no acceleration case. Okay. So that's the first half of the journey. You finish up your work on the third floor, and you get into the elevator again to head back down. So again, elevator sitting at the 3rd floor, you get in, it's not moving. But sometime later, we are again moving at a constant v downward, which means to go from not moving to the constant velocity, somewhere in there we had to have a downward acceleration. And again, while we pass the 2nd floor, because the elevator's just kind of happy and cruising and making the way down safely, we have a spot where the acceleration goes to 0. And then, of course, we don't want to crash into the 1st floor. We want to slow to a stop, which means we have to go from having a velocity downward to no velocity, which means we need an acceleration upward to cause that change. So in an elevator's round trip motion, there are 2 times when the acceleration is upward. That's when it's leaving the 1st floor to go up, or when it's approaching the 1st floor, slowing to a stop. Midway through the journey, the acceleration will go to 0 in both the upward and the downward portion of the trip. And there's 2 spots where the acceleration is downward. As you approach the 3rd floor, slowing to a stop, and as you leave the 3rd floor, heading downward. Okay, so now, got an idea of the motion. Let's do our calculations. So we got a 60 kilogram person. We've got our free body diagram here. This free body diagram doesn't care where the acceleration is, if it's upward or if it's downward. Nothing changes about it for any of these 3 questions. Okay, so if it's accelerating upward, so we have the normal of the scale on the person and the weight of the earth on the person. And let's get something out of the way really quick because we're going to need it a lot. Remember, this is mg, which is 60 kilograms times 9.8 meters per second squared. And 60 times 9.8 is 588 newtons. The other thing we know is we are accelerating upward, and that acceleration is 2 meters per second squared. When you work Newton's second law problems, the easiest thing to do is to define your coordinate system such that the direction of the acceleration, which in this case is upward, is your positive direction. You can work it the other way. You can put your acceleration in any direction you want. But mathematically, it works out a little bit better if you match the direction of the acceleration to the direction that you define as positive. Okay, so now Newton's second law, F net equals ma. I'm going to take and redefine F net in terms of the 2 forces on my person here. I'm going to take every force in the positive direction, so that would be the normal force, and any other forces that might be upward, but I only have one in this case. And then I'm going to subtract off all forces in the other direction and let that equal ma. So in this case, NSP is going to equal MA plus WEP. Remember, MA is going to be 60 kilograms times 2 meters per second squared plus 588 newtons. Okay, 60 times 2, remember that's going to be 120 newtons plus 588 newtons. So 120 plus 588, survey says, is 708 newtons. Okay, so when the elevator is accelerating upward, the normal force is greater than the object's weight. Okay, repeating, when it's accelerating upward, the normal force exceeds the object's weight. Now let's think about the constant velocity case. Okay, redrawing my free body diagram just because it's good to have it to refer to. Here, acceleration equals 0. Okay, well, I said in the last slide, let your positive direction be the direction of the acceleration. Well, there is no acceleration, so it doesn't matter. Choose a positive direction. I'm going to choose downward. So F net equals MA. In this case, I'm going to take all the forces in my positive direction, which in this case is the weight, subtract off the forces in the opposite direction, and set that equal to MA, which in this case is 0 newtons, because the acceleration is 0, which means that the normal force equals the weight, which equals 588 newtons, as we found in the previous slide. So when the acceleration is 0, when the elevator is moving at a constant velocity, the normal force equals the weight. And lastly, let's do the accelerating downward case. So in this case, normal force upward, weight downward, acceleration is downward, therefore I'm again going to choose positive downward. So I have all the forces in the positive direction. Let's not start there. Sorry. Let's start with Newton's second law. F net equals MA. Now take all the forces in the positive direction and subtract off all the forces in the other direction. And that equals MA. So in other words, the normal force is going to equal the weight minus MA. Using the numbers we found 2 slides ago, that was 588 newtons minus 120 newtons. So 588 minus 120 is 468 newtons. Okay, so 2 comments. When it's accelerating downward, we see that the normal force is less than the weight. Now, usually in a class, I have students not like this. Why not? Well, I changed my positive direction. How can I compare this slide to the one 2 slides ago when I changed my positive direction? I'm playing with the coordinate system. Okay, so let's pause a minute. And before we move onward, let's reverse the coordinate system and make positive upward again. Okay, well, if I do that, I get F net equals MA. So I have all the forces in the positive direction, subtract off all the forces in the negative direction, and that has to equal MA. Or in other words, NSP equals MA plus WEP. And now you're going to look at me and you'll be like, but Dr. Murphy, that's not the same equation you just found a moment ago. Okay, sure. But when I plug in numbers, the mass is 60 kilograms, and the acceleration isn't positive 2, it's negative 2. Because up is positive, my acceleration is downward. Weight is still a plus, so that's still 588 newtons. And I am back to 588 minus 120, which returns me to 468 newtons. So it doesn't matter. Define the acceleration in the define your positive direction in the direction of the acceleration, and it works. It gives you the same answer. Okay, now let's take our results from the last 3 slides and go back to here for a minute. And what we find is when the acceleration was upward, the normal force exceeded the weight. And that was when A was up. When A was 0, the normal force equaled the weight. And when A was downward, the normal force was less than the weight. If, oh, I have an equal sign. We'll just go equals downward. It works. If what I'm saying is true, if what I'm saying is true, then when I get on an elevator on a scale, I should see the reading on the scale fluctuate. I should see when I first start moving upward from the first floor that the needle will bounce upward. It will then come back down to its pre-motion value and then move downward as I slow to the third floor. And it will reverse that process as I come back down. Well, you guys know I'm a nerd, so guess what I did? I got on a scale in an elevator. Hold on. Okay, it landed in the wrong window. So there we go. What I'm going to do, guys, is I'm going to mute it because it's very loud, and I'm just going to narrate it for you. So here you can see me standing on a scale. This is the elevator in Bird Science Center, and it's reading about 130 pounds, which is roughly a 60 kilogram person. Now, the thing is, we may not, I don't know what the acceleration of this elevator is, so I don't know, I don't know if the numbers we calculated, if we converted the newtons to pounds, if it would actually match this, but the general idea will. So the first thing we will see after the elevator starts moving is the needle move upward towards 140. It will then come back down right around 130. And then as we slow to the third floor, it'll dip down below 130 and then come back up to 130 after it stops. And it will reverse that process on the way down. So let's see what happens. So here we are in the elevator. You can see my shadow a little bit pressing the button. So there it goes upward to 140. It comes back down to where it started roughly. I mean, it's not the smoothest elevator in the world. You can see that showing. And then as it slows to the third floor, you'll see it dip downward towards 120 and come back up. And there's a bump, which is what that big jump in the needle was. Right? Now I had to wait for the door to open and then the door to close. And I'm sorry for the poor cinematography, but I was just holding the camera above. So as I press the button and it starts moving, we should see the scale move downward. Comes back up to its normal value, or its stationary value, if you will. And then as we approach the first floor, the needle will move upward towards 140 again until the elevator comes to a stop. Doing exactly what Newton's laws predicted. And see, I'm not the only one who rides a scale in an elevator. So, one final question in this particular unit, and that question is, does the normal force have to equal the object's weight? Right? Did the normal force from the scale acting on the person have to equal the weight of the person? And I think we fairly conclusively just proved that this is a big old no. It doesn't have to be equal. It can be equal. The only times it will be equal, so equal when A equals 0, which implies a constant, possibly 0, but not necessarily 0, constant velocity. That's the only time when those two forces will be equal. In the next unit, we're going to work through a couple of additional examples regarding Newton's second law.